All right. So here we had 80% of people saying choice A, and I agree. Choice A has two things going for it. Well, actually, it has one thing going for it. So they're both linear. So the shape is out, but A has more carbons and hydrogens. So since A is bigger, it has stronger intermolecular forces, which means it has stronger intermolecular forces, which means it has a higher boiling point, which means, yes, it takes more energy to break apart its forces. All right, last one. So here I'm just going to draw the molecule. So molecule A is called 2,2-dimethylpropanol, and it looks like CH, CH3, 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 CH3. Versus good old butane, carbon, 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 and again, a bunch of hydrogens coming off of that. So let's relaunch this poll. Which one do you think has stronger intermolecular forces? Molecule A or molecule B? We'll do the final 10-second countdown here. All right. So 88% of people think molecule B. I agree. Why? More linear. Remember, we said that shape matters. And so the more linear you are, the stronger your dispersion forces are. And sure, molecule A is a little heavier because it has more carbons, but it is shaped like a circle. Molecule B is shaped like a line. So in this case, B wins because their weights are relatively the same. And so when your weights are relatively the same, you're going to look at the shape of the molecule. So that's our first question of the semester there. Any questions about how to determine which type of molecule has stronger dispersion forces? Right. If not, we can move on to our next type of intermolecular force. So we're going in order of strength. So dispersion was the weakest. Our next intermolecular force is stronger than dispersion. So our second type is called the dipole. And for dispersion forces, we said only non-polar molecules can have this. Or sorry, for dispersion, we said all molecules can have this. For dipole, only polar molecules can have this. So that leads us to a discussion. What is a polar molecule? And again, this is from Gen Chem 1. So I am not going to go over it in the depth that was covered in General Chemistry 1. What I will do is that I will put in my video lectures from Gen Chem 1 that cover that subject for you to review if you don't remember. Also, your ebook, go to the section on polarity. But what a polar, and I'll explain it briefly. What a polar molecule means is that you have a permanent dipole. That is, you have an permanent unequal distribution of electrons. And there are two things that determine this: electronegativity and shape. And so let's go down the rabbit hole a little bit more. So to have a polar molecule, I need to know electronegativity. So, of course, there's another definition. What is electronegativity? Electronegativity is basically how much an atom wants an electron. Right, so if I were to say an atom is very electronegative, that means it really wants extra electrons. And if I was going to look on the periodic table, so here's my drawing of the periodic table. The top right corner of the periodic table is electronegative, so more electronegativity, more electronegative. So your highest electronegative atom is fluorine. Fluorine wants electrons the most. Your second most electronegative atom is oxygen. Oxygen really loves electrons. So let's think about a very common polar molecule. Everybody's favorite molecule in the world, water. So water is shaped like this, and it has two lone pairs. That's what these dots mean. Those are lone pairs. And lone pairs are just electrons. So you have two electrons right here, two electrons right here. And so we just said oxygen is the second most electronegative atom that we know of. So what's going to happen is I'm going to draw this funky looking arrow. This funky looking arrow, what this says is that this is showing you the movement of electrons, basically. What that is saying is that the electrons want to go to the tip of this arrow. So your electrons are mostly going to be at the tip of the arrow. And you noticed, hopefully, that on this funky little arrow, I put a plus symbol. That means there's not no electrons, so not many electrons. The electron density is low, is how I would actually say it. But we can think, okay, by the oxygen, we have a lot of electrons. By the hydrogens, we don't have many electrons. And this is permanent. This distribution of electrons I just drew, that's water will always have that. And so this is what we call a dipole or polar molecule. Yeah. So that, in essence, is the majority of, it's not everything, but it's a lot of the important things that you should have taken away from Gen Chem 1. I know some of you have not taken Gen Chem 1 in years, which is hard. Some of you might have struggled with this and don't remember it. So like I said, I will put up some videos, and I also have a worksheet kicking around from Gen Chem 1 that will walk you through how to determine if a molecule is polar or not. But let me pause right here. That's a lot of information. Any questions about any of that terminology I just said about polar molecules? We're not even talking about intermolecular forces right now, but any questions about like polarity, polar molecules, or anything like that? Are polar molecules more likely to form IMFs? Every molecule has IMFs. The correct way to say it is that polar molecules have stronger intermolecular forces. They have dipole-dipole, which is kind of going back to the topic we're talking about before I get that aside. So yeah, I know I took a strong left turn off the road there, but let's get back on the highway. Remember, our topic is intermolecular forces. And just to give you a little recap, where was I? Yeah, so dispersion. All molecules have dispersion forces. They are the weakest. If you are a polar molecule, you get to have dipole-dipole interactions. These are stronger than dispersion. And the way they work, we just talked about water. So water has a negative dipole by the oxygen and a positive dipole by the hydrogens. So when two waters interact, the oxygen of one water will form an intermolecular force with the hydrogen of another. Right? Again, remember in chemistry, opposites attract. So the negative oxygen is going to interact with the positive hydrogen. And these dashed lines are your intermolecular force. I can show another example. C double bond O. That is a polar molecule. The oxygen is going to have the negative bit. The carbon will be the positive bit. So when two of these molecules interact, again, it's going to be that the carbon of one molecule interacts with the oxygen of another because they're opposite charge. Leave that. So that carbon was partial positive. Its oxygen is partial negative. That's a dipole-dipole interaction. Two polar molecules interacting with their opposite poles coming together to form this force that makes them stay together. Remember, that is what an intermolecular force is. It's two atoms interacting and sticking together. The stronger this intermolecular force is, the stronger they stick together. So that's our dipole-dipole interaction. Any questions about the dipole-dipole interaction? Okay. If you do have questions and you're still typing out, let me know. Or you can always email me after class. But let's go on to our next strongest. Remember, we're going in order of weak to strong. So our next type of intermolecular force, the third, is called the hydrogen bond. This is a special dipole-dipole interaction. And this is actually stronger than the dipole-dipole. All right. And so how do we know if we have a hydrogen bond? So we need to look for two things. So the first thing we need to look for to determine if we have a hydrogen bond. So these are things to look for. The first thing to look for, do you have a polar molecule? Right? Hydrogen bonds can only occur between polar molecules. Second, if you have a polar molecule, do you have an oxygen bound to a hydrogen? Or do you have a nitrogen bound to a hydrogen? Or do you have a fluorine bound to a hydrogen? If you have one of these three bonds, you can now create what's called the hydrogen bond. And so let's go back to water, because what I actually drew for dipole-dipole for water was a hydrogen bond. So here we have water. Again, it's a polar molecule. Our oxygen is partial negative. Our hydrogens are partial positive. So that's our first thing. Okay, we have a polar molecule. Then we look at what type of bonds we have. We have an oxygen bound to a hydrogen. Okay, that's our second criteria. So water can form these hydrogen bonds. And all a hydrogen bond is, it's a dipole-dipole interaction meeting these criteria. So here I have a hydrogen of one water interacting with an oxygen of another. So yeah, technically, this is a type of dipole-dipole, like we just talked about. However, it has upgraded strength. It is stronger. Strength, E-N-G-T-H. Because it has this special oxygen-hydrogen bond. So these are actually stronger than normal dipole-dipole interactions. One thing I want to mention, those of you who need to take biochemistry for your degrees, and if you are going to take biochemistry here, you get to hear my lovely voice again, because I am a biochemist. Inside of your cells, you are 70% water. So the majority of life inside your cells, the majority of interactions are hydrogen bonds. And what drives me crazy is when I get people in biochemistry, even though I mentioned this again, carbon bound to a hydrogen can never, ever form hydrogen bonds. Because carbon bound to a hydrogen, that is not polar. It will never be polar. So that's a fast trick for you. If you see carbon and hydrogen in a covalent bond, you know that is not polar. And so the only forces it could have are dispersion forces. And so if I ask you a question on the test, which I'm likely to do, and I give you a molecule, and I say, I don't know, does this have hydrogen bonds, or point at the hydrogen bonds? And it has carbon and hydrogen bonded together. Ignore it. For a hydrogen bond, hydrogen has to either be bonded to oxygen, nitrogen, or fluorine. A stupid mnemonic for this is hydrogen is fun. It's supposed to be fun, but we need to use oxygen. That is a way to remember this. Hydrogen is fun. So if hydrogen is bound to oxygen, nitrogen, or fluorine, you can have a hydrogen bond. If it's not bound to one of those three, you cannot. So that is the hydrogen bond. Questions about the hydrogen bond? Right. Let's move on to our next strongest interaction. Our next strongest interaction is called the ion dipole. And so we need to talk about ion for a second. Again, this is a term back from General Chemistry 1. An ion is a molecule that has a formal charge. That has a formal charge. So it has a charge of like -2 or +1, right? What a formal charge means is that the number of electrons does not equal the number of protons. So the number of electrons does not equal the number of protons. That's an ion. You have two forms. You have a cation and you have an anion. The way I remember this, here's my drawing of a little cat. Cations are positive, right? Supposed to be positive. So cations are positive. That means that the number of protons they have are greater than the number of electrons. So that's how I remember that. Cat, positive. Anion. I don't have a fun animal for this, but the way I heard somebody say it before is a negative ion. Anion. So here you are negatively charged. That means the number of electrons you have is greater than the number of protons. You have a negative charge. Cation, you have a positive charge. All right. So that's an ion. So what's an ion dipole interaction? So this is between an ion and a polar molecule. So imagine that we have table salt. Table salt is made out of NaCl. And I'm going to put that salt into a glass of water. So you probably know what's going to happen if I put this solid salt into water. It dissolves. It disappears from our view. And now we can understand why that salt dissolves. So when that salt goes into water, it splits into ions. So our salt, sodium, is a metal. Chlorine is a nonmetal. When you add a metal and a nonmetal together, that's what we call a salt. Or, again, back from Gen Chem 1, we call this an ionic bond. So we have an ionic bond. When we put an ionic bond in water, the ionic bond breaks and you form ions. The metal will always form your cation, so it has a positive 1 charge. The nonmetal is your anion. It will form a -1 charge. So when I put this salt in water, well, water has a dipole. Water is polar. And so what will happen is that the negatively charged oxygen of water will surround the positive sodium. Remember, these dashes I'm drawing, these are your intermolecular forces. So here is one ion dipole interaction, the positive sodium interacting with our water. The negative chlorine, well, since it's negative, the hydrogens of water, remember the hydrogens of water are partially positive, they will interact with the chlorine to form another ion dipole interaction. So that's ion dipole. If I put an ion into water, or if I put an ion into a polar solution, the polar molecules will surround that ion. It will form these ion dipole interactions, and they will be very strong. So that's our fourth type of intermolecular force, the ion dipole interaction. Questions about that interaction or that intermolecular force? All right, only one more force to go, but let's recap. Our weakest force, dispersion. All atoms have this. If you're nonpolar, this is the only one you have. Our second force is dipole-dipole. Only polar molecules have this. Our third force was the hydrogen bond. Only polar molecules that have a hydrogen bound to fluorine, oxygen, or nitrogen have this force. The force we just talked about is the ion dipole force. This is when you mix an ion in a polar molecule. The last type of intermolecular force we can have is called the ion-ion. Or, as we just said on the previous page, this is called the ionic bond. And so I form an ionic bond when I take a metal so sodium, and I mix it with a nonmetal, chlorine. And what happens is that when these two come together, and actually let me draw out the Lewis structures. Again, this is a blast from the past from Gen Chem 1. So sodium has one electron in its Lewis structure. It has one electron in its outer shell. Chlorine has 7 electrons in its outer shell. And remember, electrons want to form an octet, or sorry, atoms want to form an octet generally. So what happens is that sodium gives an electron to chlorine. So sodium lost 1 electron, so it became +1. Chlorine just gained an electron, and so it becomes -1. And now you have these two atoms. One's positive and one's negative. We know that opposites attract in chemistry. And so the sodium will interact with the chlorine. They will come together. And so if I was going to draw this, we could see something like this. We have the positive sodium having an intermolecular force with the negative chlorine. This is the ion-ion interaction, or as we call it, the ionic bond. This is incredibly strong. The boiling point of ionic bonds are massive. Remember, we said about an hour ago now, the higher the boiling point, the stronger the intermolecular force. And so if you were to take some table salt and put it in a pan, and then put that pan on your oven and turn it to the highest temperature you can, you would not melt that salt. It's too strong. You'll just get hot salt, but you'll not get liquid salt. To get liquid salt, you need extremely high temperatures. I don't know the number off the top of my head, but I want to say it's like 1,000 or 2,000 like Celsius. Might not be that high. It might only be like 800 Celsius. But even so, that's incredibly hot. So these ionic bonds want to stick together. But yeah, that's an ionic bond. If you have a metal and a non-metal coming together, you form an ionic bond. So those are our 5 types of intermolecular forces. So just to recap, again, we're going to be using these intermolecular forces a lot. So from weak, the weakest is dispersion, followed by dipole-dipole, followed by the hydrogen bond, followed by the ion dipole, and then the strongest is the dipole-dipole. Or sorry, not the dipole-dipole, the ion-ion. So we're going in order from weak to strong in this list. All right, so those are the 5 intermolecular forces. So, any questions about those intermolecular forces? All right, so what we're going to do now, it's question time. Yay. So our question 2, the second question I'm going to ask you for this semester, is I want to know, based on the molecule, what type of intermolecular forces? Actually, sorry, I'm gonna change that a little bit. Based on the molecule, what is the strongest IMF possible? So I'm going to give you a molecule. Possible. I don't know how to spell. That's okay. This isn't English. I'm going to give you a molecule, and then your choices, I'm going to pop up a poll again. So choice A will be the strongest possible is dispersion. Choice B would be dipole / dipole. Choice C would be the hydrogen bond. Choice D would be the ion dipole. Choice E would be the ion-ion. So your first molecule that I want you to try and figure out is N2. So I'm going to draw you the Lewis structure. So there are two molecules of N2, and there's its intermolecular force. So let me pop up the poll, and I want you to tell me this intermolecular force between two molecules of N2, what is the strongest intermolecular force that you can have? And let me just... Yay, I have to remake the poll because it just crashed. So choice A, B, C, D, E. All right, there we go. So for N2, what is the strongest intermolecular force it can have? Will it have only dispersion? Will it have dipole-dipole? Will it have hydrogen bonds? Will it have the ion dipole or the ion-ion? Take your best guess. If you're not sure, that's okay. I will explain how we get to the answer after you've thought about it and took your stab at it. Let's do like 15 more seconds. At this point, just give your best educated guess. That's totally fine if you're wrong. That's how we learn, by being wrong. All right. We'll share those results. So the majority of people think it's A, a smattering of people B, and then one person C. The correct answer is A. How did I figure this out? All right. So if a molecule, or if an atom rather, if an atom is bonded to itself, it is nonpolar by definition. And the logic is, remember, polar means you have an uneven distribution of electrons. However, if two nitrogens who have the same, they're clones of each other, right? So they have the same electronegative force. If they are trying to take electrons from each other, they can't. And the way I always think about this is, oh, I just lost my train of thought, but tug of war, there we go. So imagine that I have a clone of myself. We both have a rope, and then we're trying to pull the rope from each other. Well, if it's me, we have the same strength, so the rope doesn't go anywhere. That's the same with electrons. So if an atom is bonded to itself, it is nonpolar. If it's nonpolar, it only has dispersion forces, right? So that's a quick way for you to determine if a molecule is nonpolar or not. Is it only made out of one type of atom? Nonpolar. Right, questions about our first prompt there? All right, prompt 2. And yeah, if you have a question, but I went a little too fast, that's fine. You can feel free to answer or keep asking it. Our second question, NH3. So I have 2 molecules of NH3 interacting with each other. That's basically what NH3 looks like. I want to know, what type of intermolecular force do two molecules of NH3 have? Do they have A, dispersion? Or what's the strongest, rather? A, dispersion, B, dipole-dipole, C, hydrogen bonds, D, ion dipole, E, ion-ion. Let's do 15 more seconds here. All right. So the majority of us, roughly 90%, think it's hydrogen bonds. I agree. Remember, hydrogen is FON, F-O-N. So if you have a hydrogen that's bound to a fluorine, to an oxygen, or to a nitrogen, for the most part, you have access to a hydrogen bond. Usually, if hydrogen is bound to one of these 3 molecules, you are polar to begin with. Not always. There are some exceptions, but usually. So it's a pretty safe bet that we have hydrogen bound to nitrogen. That's a polar molecule. And yes, you get hydrogen bonds. That's your strongest. All right. Let's go to C. C is carbon monoxide. That's what carbon monoxide looks like. So I want to know, when 2 molecules of carbon monoxide are interacting, what is the strongest type of intermolecular force I could expect to see? A, dispersion, B, dipole-dipole, C, the hydrogen bond, D, ion dipole, or E, ion-ion. Let's do another 15 seconds. All right. So we have the majority of people saying B. I would expect the dipole-dipole, a handful of dispersion, and then an ion-dipole interaction. And the correct answer is B. Why? Carbon and oxygen is a polar bond. Right? That goes back to electronegativities, but that is another thing, especially those of you who want to go on to organic. That is something you want to kind of have down in your head. Carbon and oxygen together, when they're bonded, is polar. So oxygen has that partial negative, carbon has that partial positive, and so we have a dipole. However, there's no hydrogen, so it's not a hydrogen bond. There's no ions either. So to have an ion dipole, you need an ion. I need to draw you an ion, something that has a plus or a minus charge. I didn't, so this is simply dipole-dipole, B. All right, last one. The last one is carbon tetrachloride. So carbon interacting with 4 Cls, or bonded to 4 Cls. So when 2 molecules of carbon tetrachloride interact, oops, I drew my C too early. What type of intermolecular force, or what strongest intermolecular force would you expect? And my L kind of bled in, so that's the IMF there. Would you expect dispersion, dipole-dipole, hydrogen bonds, ion-dipole, or the ion-ion, or carbon tetrachloride? Let's do another 15 seconds here. If you haven't answered yet, take a stab at it. What does your gut tell you? If your gut's not telling you anything, pick your favorite letter, I suppose. All right. This one, I'll share those results. We have, we don't have a overall 50% answer. The majority of people, though, said A. I agree. Let me just talk about why D's wrong. Again, you cannot have ion interactions unless you have an ion. And let me just draw that so we're completely clear. If I was to give you an example of ion, I would have to give you a little molecule and tell you its charge. So that's an ion. And so Here's an ion dipole for you. I gave you a molecule with a little charge. It's interacting with a polar molecule. But if we look, nothing has a charge. I didn't write a little charge symbol. So since I don't write a little charge symbol, throw away the ions, right? Only do the ion answers if you see an ion. Nobody said C. That's good because we don't have hydrogens. So it comes down between dispersion and dipole-dipole. It comes down to, do you think this molecule is polar? Here's another hint for you. If carbon is bonded to 4 of the same element, it is nonpolar. Right? So carbon is bound to 4 different chlorines. By definition, that makes that molecule nonpolar. So that's another way to do these fast. If you see carbon and it's bound to the 4 of the same thing, nonpolar. If you see hydrogen bound to NO or F, or FON, I guess, it's polar. If you see carbon bound to oxygen, or if you see carbon bound to nitrogen, or you see carbon bound to fluorine or one of the hydrogens, it's usually polar, unless it's bound to 4 of the same things. And one more hint for you to do these fast. If carbon is bound to hydrogen, it is nonpolar. Right? So these are kind of the tricks. I can stop sharing that. You don't need to see that. These are some of the tricks you can have in your head to kind of memorize, really, to know if you're looking at a polar or non-polar molecule. So let me just make that list a little bit neater. So some tricks. So non-polar. Molecule bound to itself. For example, O2, N2, H2, those are nonpolar. Carbon bound to hydrogen, that's another example you're going to see often. Carbon bound to 4 of the same thing, the same element. Same element. So what we just saw, carbon tetrafluoride, is nonpolar. Sorry, I'm running at an angle there. Polar. Oh no, I'm running out of lines. Polar. Basically, carbon, oxygen, carbon, nitrogen, carbon, fluorine, hydrogen, oxygen, hydrogen, fluorine, hydrogen, nitrogen. These are the very common ones we see, especially organic chemistry, biochemistry, general chemistry. These type of interactions. Ion, you're looking at a metal plus a non-metal. This list is not exhaustive by any means. Again, after today's class, what I'm going to do is I'm going to post some videos about if a molecule's, how to determine if a molecule is polar or not. And I'll also give you that worksheet there. CCl4 is dispersion. Yeah, so that was dispersion. And like I said, these slides will be available in case something does happen. I will post these online after our class is done. But any questions about looking at a molecule and determining whether we are determining what type of intermolecular force is the strongest here? All right. This last one, dispersion. CCl4 was dispersion. Oh, you mean if you're looking on the actual slides, there is ESiH4, that's dispersion as well. But yeah, I skipped that one because it's the same one as D. Yeah, E was dispersion. All right. So with that, I'm actually going to go if you have the slides in front of you, the next set should be dipole moment. I'm actually going to skip that and just jump into our next topic. I know this is a lot, but like I said, each one of these classes is a week of normal classes. So it's a lot of information. So the next thing we're going to talk about are IMFs and solubility. And solubility, means dissolving. And for here, we have two terms that we're going to learn. The first term is hydrophobic. And the second term is hydrophilic. So hydro, just since we are learning a language, and I believe this is Latin, hydro basically means water. Phobic basically means scared or afraid, right? You have a phobia of something, you're afraid of something. Philic basically means love, right? Philadelphia is made out of philic in Delphi. Philic means love, like Delphi means brother. That's why it's called the city of brotherly love, right? Philadelphia. Here, hydrophilic means water loving. So whenever we see the term hydrophobic, all that means is that a molecule is nonpolar. Whenever we see the term hydrophilic, that simply means the molecule is polar, right? So that's all that means. Hydrophobic means you're nonpolar, or hydrophobic means nonpolar, hydrophilic means polar. And so we are going to connect that with solubility. And the phrase that people have to remind themselves of this is like dissolves like. What that means is that polar molecules dissolve or are soluble. When I say soluble, that means they can dissolve in. Polar molecules dissolve or are soluble with other polar molecules. Nonpolar molecules dissolve nonpolar. Whoops. You cannot mix them. By that, I mean polar does not dissolve nonpolar. And we probably have an idea of this already, because we have a very common phrase in England, or English, not England. They're like oil and water. So if I try to mix oil with water, they will form two separate layers. They do not dissolve. When something does not dissolve, if they form two separate layers, we say that is immiscible. These things are immiscible. Immiscible means they don't dissolve, so not dissolving, not soluble. And then on the other side, if things are miscible with each other, they are soluble, right? And so whenever you see a word starts with IM, usually that means not, right? Think about the word impossible, not possible, right? It's the opposite of possible. So immiscible, not miscible. And why aren't these things miscible? The reason why is that they have different IMFs. Right? Remember, oil or nonpolar, so if you didn't know, oil is nonpolar. So nonpolar molecules only have dispersion. Oh no. That's the bad things of having a 2.5 hour class. I've never run on my page limit before. One sec. I'm just gonna erase. Oh, what to do? Okay, I'm just gonna create a new one. Whiteboard. All right. Sloppy, I know. I apologize. So, oil, water. These are immiscible. Right? Oil, nonpolar. And when you're a nonpolar, the only type of intermolecular force you have are dispersion. That's the only one that you get. Water, which is polar, you get dispersion. You get dipole-dipole. You get hydrogen bonds. And you could have ion dipoles, right? If you put an ion in the water, but water by itself just has these three. And so imagine if oil and water mix, what would happen? If these two mixed, well, oil still has its dispersion, right? But water would only have dispersion as well. Because remember what we talked about, and I know it's been a lot, but when we talked about water, to form that hydrogen bond, right, you had two dipoles interacting. So that's a hydrogen bond, and it's strong. It's very strong. However, if the water interacted with oil, let's just make our oil super simple. The IMF it can only have is dispersion. Remember, dispersion is weak. And in a rule of thumb, the rule of thumb is molecules want their strongest IMF. So water can hydrogen bond. So in general, it's going to try and interact with other molecules that can hydrogen bond. Or at the very least, it's going to interact with other dipole molecules, because at least you have a strong interaction there. Dispersion is incredibly weak. And so water does not want to interact with something that only has dispersion. It's missing out on interactions. It's missing out in energy. So and you can try this at home. It's actually a very cool little experiment. If you have a glass of water, pour some olive oil into it from like a little bit of height. What you'll see is that oil will drop in the water, but it'll be like a perfect sphere, more or less. And then it will shoot back to the top of the glass. Why? Because all of that water is working together to push the oil away. Because if it was going to interact with the oil, it would only be able to do so through dispersion. While if you push the oil away from yourself, and if you interact with water molecules, then you get hydrogen bonds. So that is what determines whether two things are miscible. It comes down to polar molecules interact with polar molecules. Why? Because you get access to stronger intermolecular forces. All right, so I think I'm going to put a pin right there. Any questions that anyone might have on top of their head about the myriad of information we covered today? And if you do have questions, but you're too burned out from listening from me talking 2.5 hours, I know my throat is feeling scratchy from 2.5 hours. That's fine. Email me later. Remember, your first homework will go up today on Pearson. The video I made going over how the class works will go up as well. I will put up your the polar material from Gen Chem 1. So your tasks for me are your Pearson homework. Sign up for Pearson. Do the homework assignment. Do your welcome survey. That shouldn't take too long. Do your pre-class assignment for Thursday. And also understand how polar molecules work. And review what we talked about today. And that's what I want you to do before the next time I see you. Reminder, I will be on campus and I will be in our classroom on Thursday. So I do invite you to come and join. Otherwise, I will have the Zoom up in the same Zoom area or same location as today. Otherwise, welcome to summer, everybody. And I will see you Thursday. Have a good rest of your day.